In the previous class, we are done with the bulk metal forming operation, right? Now we are going to discuss sheet forming operations. That the only difference between bulk and sheet metal forming is nothing but the thickness of sheet is very smaller. I mean, the length to thickness ratio is very high, or thickness to length ratio is very small. You can say T by L ratio is very small. Compared to the length, your thickness is very small. That is what is meant. I mean to say is that the thickness is very small before and after forming operations. So you might ask, sir, in rolling also we had very lesser thickness, right? So it also comes under sheet metal operations. No, because we are taking a big bulk material there and then we are converting that into some kind of a sheet. But here it's not that. We are taking the sheet itself and then we are trying to form that sheet into different shapes. Now that we understand the difference between bulk metal operation and sheet metal operation, I mean forming operations. So there are different type of forming operations here. The diagrams are very well put here. So V bending, you can see that there is some kind of a V die here. There is a die on which a V-shaped hole is punched onto that, or maybe a dent of V shape is there in that, and a sheet is placed upon that, and then we have a punch. The help of punch will be able to apply the force onto the sheet, and then the sheet takes this kind of a form and it turns into a V shape, right? So this is called a V bending. It means that you are trying to bend the material. If you are trying to bend, if you are done with this set of materials in bending, what did you see? You had some kind of cantilever beam. If you remember, you had a cantilever beam like this, and then you are trying to apply some transverse load T, and then you see it's going to bend. And but after removing the load P, it will come back to its original position because you are trying to deal with the elasticity there. As I told you, strength of materials will come under theory of elasticity, and metal forming comes under theory of plasticity. So we have to have permanent deformation. That is the reason why we are trying to apply force in such a way that the deformation what we are trying to achieve is permanent. Okay, so this is what is bending. Let's discuss a little bit of more on bending in the coming slides. And in bending also we have another thing, that is edge bending. This is similar to the cantilever beam example, right? You have some kind of fixed support. Let's assume that this is kind of a fixed support. With the help of pressure pad, you have a die here, and you are putting some pressure pad on that, and you are trying to lock this sheet here, and then you are trying to apply transverse load with the help of this punch, right? And it's going to make this kind of a edge bending, because this is called edge bending because you are trying to bend with respect to this edge here. This is the edge where you are trying to bend, right? And the other sheet metal operation, the example of sheet metal operation is shearing. Shearing in the sense you are trying to cut off. You instead of trying to apply a blunt edge here, you are trying to apply a blunt punch here. So that this will not it will only deform. It won't cut away, right? It won't shear. It only deforms. But here you're trying to cut it off, like you're trying to punch hole up to that. Like what you say, like if you have a paper and you have a punching machine, right? You're trying to punch it off. In the sense, you are trying to create some holes into that paper. In the same way, you are trying to create some holes, or maybe you're trying to create some kind of a design onto the sheet by making holes, and that is called shearing operation. Shearing in the sense you are cutting it off, right? It's kind of a scissor also is scissor. You have scissor, right? So what does scissor do? It shears. Like if you have some object in between a scissor, and then if you are trying to it's called cutting, but whatever the operation that is occurring is called shearing. Okay, so sometimes I will even make this kind of funny statement that buy a piece to shear, or it should be a shearing shop, because the operation, even though we call a hair cutting, hair salon, whatever it is, but the operation in between the scissor is shearing operation, because you are trying to apply a parallel force, right? You are trying to apply the shear force there onto the hair there. That's the reason why it's called shearing operation. Anyways, let's not go to that. And this is one of the another sheet metal operation, that is shearing. Okay, next, these are another sheet metal operations. Flanging, you're trying to make a small turn here, and then you're trying to stretch it. This is a stretching operation. This is shrinking operation. This is shrinking operation. This is stretching operation. And hemming is like you're trying to have a bend. Seaming, it's kind of two hands, hand in hand. Another is curling. So different names are put to each and every sheet operation. No need to remember everything, but at least you just try to understand, like, these are all sheet metal operations. And another important sheet metal operation is deep drawing. Okay, in deep drawing, what do? You try to make a cup. You try to make a cup. That's the reason why it's also known as cup drawing. So deep drawing is also known as cup drawing. Why? Because you have some sheet. I'm showing the top view. If you are seeing the side view, it will be like this, right? It is having some thickness T, right? And you're trying to apply. So this is what is this? This is what is this? You have put between. You have two dies now, right? You have two dies, and the die is also in kind of a circular shape. On that, you're putting this kind of a sheet, and then you're applying some punch in between, right? When you're applying, this kind of takes this kind of shape, and that is what is shown in this figure. And this is a cup. The cup. So this is also known as cup drawing. So let's discuss all these things in detail, which is why we have to give the clearance, where tension is appearing, and where compression is appearing, what is wrinkling. All these things we'll be discussing in the coming slides. Okay. Now, okay, so it's good. So the first thing what we're going to discuss is cup drawing itself. Fine. So as I already mentioned that, so if you see the edge bending, you see the previous slide, the edge bending. So it's same like edge bending, but it's an extension that you have another, or you can have a circular die. So here this thing doesn't mean that it is two. It is like circular. Okay, you should understand that it's circular like this. This is also a circular like this. And this blank also, if you are seeing from the top view, everything looks like a circle. Okay, please do not misunderstand that this is one die, another die. It's a full circular. It's a cross-sectional view. That's the reason why it is visible like two, right? What? Now you're placing this workpiece. This is what is your sheet. You're placing the sheet, and you're holding that sheet with the help of some force, and that are known as blank holders. These are known as blank holders here. Now what you do, you try to pass a punch. This is what is punch here, and the punch is having some force and some velocity V, as it is. Like we have seen this thing in the forging operation, if you remember, right? The impact forging or whatever the forging that we have seen, it's kind of force and velocity that we have tried to apply, right? And now this punch, whatever you're trying to apply, is a little, having some corner radius R here, RP, the radius of punch, and the diameter of punch is this. Okay. And now when you apply force, you are trying to provide some kind of a clearance. So what is clearance here? Let's see that. The clearance here is this, right? This is the clearance. Why you are providing clearance? Obviously, if you are not providing clearance, then where the sheet is going to flow? If you are having this thing like this, and your punch is exactly the same dimension without any clearance here, so where the material will go? There is no space for the material to flow, right? So to make sure that the material has some space to flow, you have to provide a clearance there. So this is what is clearance. See, through the clearance only, this material will be flowing into cup. It is taken into this kind of a shape, cup. Okay. If you are seeing the three-dimensional figure, it will be something like this, right? It will be something like this. Okay. So, okay, I didn't draw the diagram properly. I'll show you. Yeah, it represents like this. It's like this. This is the cup here. I'm showing this diagram in the defects of deep drawing, but try to understand this is what is the cup. So whatever the glasses, teacups in the home we see, right? Small tea glasses and big glasses and all we see, right, in the home we use for drinking water and juices and tea and coffee, whatever it is, that are made by this deep drawing. If you understand, if you're going to interview and they ask there might be some small T class in front of them. They'll ask like, what are your favorite subjects? Then you might say, sir, I'm good in manufacturing, if possible. Okay, so then they'll just show that like, okay, this is a class. What kind of operation is used to make this kind of object? So then you should be able to approximately guess that, oh, this is okay, this is a sheet, so it's a glass, so obviously there's no possibility that it's going to be made by casting or maybe form, what you say, the metal cutting. Obviously it is made by forming. In forming also it comes under this deep drawing section, because you're trying to make a cup, right? So this is what is cup drawing. So now there are some stages in cup drawing. Before going to that, this clearance, see what you're trying to provide is not exactly. So what do you think, sir? I have this thickness T. So it's the same thickness T I'll provide as clearance, so that the same thickness only, no, it will form. No. What you do, you give a little more extra, 10%, what you say, 10% more than, it means in the sense like, if it is T, then you'll give 1.1 T as your clearance approximately, because you give little more space for the cup to flow into the die portion. Okay, now what are the stages in deep drawing? There are some few stages. We'll discuss each stage, and then we'll understand how this complete circular sheet is being formed into a cup. Okay, so what is the first one? As the punch pushes the sheet, it is subjected to bending operation. Where it is occurring? Where the bending operation is occurring? Tell me. Let me know where the bending operation is occurring. Anyone? Where the bending operation is initially, when the punch is trying to push the workpiece here, it is trying to push like this. Where this bending operation is occurring? Anyone who can just say between what and what this bending operation is occurring? Anyone, guys? Hello? Yes, between corners of punch and clearance. Yes. So this is where the bending is occurring. So this is what is edge bending. If you have seen, if you discard this section, then you see this is kind of edge bending. So there, the place where the bending operation is occurring is at this place. So this is where the bending operation is occurring, like this. Okay, fine. Now, bending of sheet occurs over the punch, a corner and die. It's already written here. We should have told this answer anyways. Okay. The outside perimeter of blank moves slightly inwards to the cup center. So fine. Now next, in second stage, the sheet region of the bend was over the die corner will be straightened in a clearance region, and the stage, so it's and at this stage, so that it will become cup wall region. In order to compensate the presence of sheet in wall cup, more metal will be pulled from the sheet edge, and now you just read all this stuff. I'll tell you what is happening. Okay, so all the steps are written here. Let's not read because it's very boring to read. So what I'll do, I'll explain all the stages and I'll come back. So the diagram is very much like this. Initially, the bending is occurring at this point, and later on in the second stage, the bending is occurring at this point, and there is some kind of a straight wall region that is being formed, and this is what is straightening here. You see, right? As you keep on going, slowly this edge is trying to move inside. You see, this edge is at this point. Now the edge is at this point. Now it is at this point. Okay. So as you keep on moving, this edge is moving. The sheet is moving inside, and the straightening is occurring, right? And the straightening is occurring. So initially, the first stage is the second stage is bending like this. This is where the bending ends. Third stage is straightening like this. Okay, that is what is written here. Okay, same thing. And the friction between the sheet and die, the blank on the surface restricts the movement of the sheet die opening, and this is where you apply some kind of, you have some frictional forces between this die and the sheet, and there is a frictional forces between the blank holding force and the sheet. Everything is there, right? There is no friction. Obviously, if there is no friction between the blank holding die and the sheet, obviously the sheet will slip away, right? That's not good. You have to apply certain force so that there should be some friction that should be exerted here, so that the sheet neither should not stuck there, nor it should not go very easily. It should go in a certain speed. Okay, certain way it has to go, but it's not completely slip. It's not completely struck. It should slip, obviously. It's not completely slip. Okay. Next. And you have to understand here, this place, this why are they saying that there is a compression and thickening of flange edge? Because if you see, when you're trying to apply some load here, the the um, the sheet will be formed like this, right? The bottom one will be formed like this. This is what is brinkling. This is what is brinkling. If you see, did you see that anytime? This is kind of sheet. So this is what is compression. Obviously, everything is wrinkled, right? Wrinkled in the sense it is compression and thickening of flange. Okay, thickening of flange, because compression is happening in like this and it is happening like this. Obviously, this thickening will happen. Okay, fine. And then after some time, if at all the friction between this and the sheet is not very high and good lubricants are provided, then what we can do, complete sheet can go inside and full proper cup can be formed without any this kind of wrinkles here. So to avoid wrinkles, you have to have proper lubrication, right? You have to have some lubrication in between the blank holder, sheet and die. Okay, are you getting my point, guys? Is it clear how this cup drawing is being performed? Very good, very good. Now, so there are some parameters that you have to try to understand. What is called a drawing ratio? Drawing ratio is, what is drawing ratio? So this kind of questions can be asked in HL exam as well, right? So they'll be saying that, okay, this is my diameter of the punch and this is my diameter of the blank. What is the diameter of the blank? Diameter of the blank is nothing but the diameter of the blank, dB, right? Diameter of the punch, this is the diameter of punch, AB. This is diameter of the punch. Diameter of the blank is this. Diameter of blank is D, right? So they might say, what will be the drawing ratio? Obviously, drawing ratio will be diameter of blank divided by diameter of punch. Very important formula that you have to note down. So please try to note down this formula if you're trying to revise this section. So this is the formula that you have to keep in your short notes. Very important. Drawing ratio, simple formula. And there can be another question that can be asked, what is the reduction? So this is the reduction. What is the reduction? Right? This is the another formula. What is the reduction? Reduction is nothing but diameter of blank. What is blank? Blank is nothing but workpiece. Please do not get confused here. Blank is nothing but workpiece. Workpiece. That sheet that you want to try to draw into a cup. This is your punch. Okay, and diameter of blank minus diameter of punch divided by diameter of blank. Okay, and this drawing ratio, the limiting values is nothing but the drawing ratio cannot increase more than 2, and the reduction cannot increase more than 0.5. So this reduction is this, and drawing ratio is, so this drawing ratio should always be less than or equal to 2, and this reduction should always be less than or equal to 0.5. That is what they're trying to say. Is it clear, guys? Okay, very good. So please try to make sure that you remember these two formulas, very important formulas, these two formulas. Good, cool. So let's proceed. Now, okay, fine. I have a very thick blank. Of course, this is another view. This is the top view, and this is the side view. This is side view, top view. So now the thickness is very high, and or maybe what I want to do, yeah, the thickness is very high. Very high in the sense not it's not categorized into bulk metal operation. It is still categorized into sheet metal operation, but the thickness is a little high, and you want to make a very deeper cup like this. So for that, suddenly you can't bring a small punch and you try to punch it, right? You can't do that, right? So what you have to do, in terms of like rolling. We have seen rolling, right? There is a big sheet and you want to convert it to very big blank. You want to convert it to small sheet like this. So what you do it in a pass, right? Either you use tandem mills, all this we have seen in the rolling, if you remember, right? In the same way, what we have to do is that you have to do redrawings. In the sense, initially you had some blank like this, and then you converted this kind of a cup. Again, you're putting that cup, this cup, and again you're making the cup into this kind of shape. So you're redrawing. So this is blank. First step, then second step. So the second step is known as redrawing. Fine. So why sir, why this why sir, why we have to redraw? Because we have seen the limitation. The limitation of drawing ratio is 2. It can't go. It means that if your diameter of blank divided by diameter of punch is equal to 2, then it's okay. If it is equal to 3, then it's not good. In the sense what? Let's say if your diameter of punch is equal to some 10 mm. Okay, let's say 10 mm. And if your diameter of blank, let's say it is 40 mm, bigger blank. Now if you want to make, what is the ratio? What is the ratio? Drawing ratio dB by dr. So dB by dr. What is dB by dr? 40 by 10. It is 4. So obviously this kind of things are not allowed. It's the maximum value is 2, right? If in such situations, what you do, initially you try to make diameter of let's say if you want to make the diameter of blank is 40, let's assume, and diameter of punch is 10, let's say. So what you do, initially you make a secondary diameter dB1, which is equal to approximately 20, right? This is what is first draw. Then in second draw again you make dB2 is equal to some more extra change. The dB2 is the diameter. I mean, from here to here the change will be some 20 again extra. So this 20 plus 20 will be 40. You're understanding, right? What I'm saying is, you're getting my point, what I'm saying? Yes. So that's the reason why, as there is a limit for the drawing ratio, or maybe the reduction ratio, whatever it is, you consider anything. That is the reason why you have to redraw. Okay. So now, what are the guidelines that you have to follow for a successful redraw? So initially what you have to do, if there is any diameter, start with some blank and then try to reduce to 40 to 45%, and then in the first draw, and in the second draw you make it 30. This 30% is with respect to the workpiece at this position. So this is your diameter of blank initial start, and this is your first position, right? So the second draw, whatever 30% should be reduced with respect to this first one. It's not with respect to the start. Okay, please do try to understand that, right? Like casting, we have seen that, like shrinkage allowances. First we try to apply the solidification shrinkage. After reducing that, on the total value of volume, what is left, you are trying to apply the solid shrinkage. Remember, in the casting, the same way, this is what we'll do. We'll reduce the first draw to be 40 to 45%, and second draw 30%, third draw 16%, and keep on going like that. As we keep on increasing the redrawing, so you see the reduction is reducing. Okay, fine. Next, what are the defects in deep drawing? Obviously, I told you these are the wrinkles. Okay, these wrinkles are formed, and which is not good. It's not good looking, right? So, and another problem with deep drawing are this thing. What you say, tearing. Some kind of, why this tearing happens? Because you're trying to apply a punch. This is your punch, and this is your the wall region of your die, and this is your punch. So because of friction between the punch and the die, and there is thickness that is being flown here. Because of that, there might be some kind of tearings happening because of your tension in that, or maybe compression in that, right? So that is what is tearing. Okay, and earrings are like on the top of cup. It's not exactly parallel. It might be having some waviness, and that is called earrings, because that is resulting because of the planar anisotropy of your material. Let's not go deeper into that. This is the reason why these earrings are happening. And surface scratches is obvious because of the friction. There is no what do you say product which will get without surface scratches. But if you are providing proper lubricants and all, the scratches might get reduced, because you see that because of pure lubrication only, this kind of surface scratches are occurred. Okay, so these are the defects of deep drawing. Okay, and this is how the question is being solved. This is I think this is a previous engineering service examination question, but let's not discuss that here. So nothing, they are trying to ask, like there's a blank here and they are trying to draw into cup here. So then they are asking what will be the, how many draws are necessary, how many times you have to draw the drawing, so that at the end you get whatever that you want to acquire. Okay, fine. So this is at the finally they found out the total amount of draws are 6. Okay, now next one is sheet bending. So we have seen already in the initial slide of our sheet metal operations bending itself, right? So bending, obviously we have seen in a theory of elasticity, or maybe in strength of materials, you might have seen these things. Let me discuss it again. Here, this is a sheet. This is a sheet, and it is having some thickness T. Okay, fine. Now we have, what is this? This is an axis. An axis, and when you are trying to apply some kind of cantilever load here, and let's say this is fixed here. Let's say this is fixed here, and this is trying to bend like this. This is trying to bend like this, and this is the axis which is bent like this. Okay, so the topper portion is attained. It's getting, or maybe it's getting stretched, right? It's getting stretched, and the bottom portion will try to compress. If you are seeing the pure bending diagram, it will be like this, right? The bottom portion will be having compression, and the top portion will be having tension. Yes, right, tension. And there is one plane. There is one plane. This is why it is called plane, sir. This is not a line, because this is not a tooth diagram. It is a 3D one, right? So there in between there is one plane. There is one plane, such a plane that the initial dimensions and final dimensions, even after the bending, will be same. So the initial dimension, let's say the length is L here. After bending, the top portion will have some length plus delta L, and here bottom will be L minus some delta L2. This is, let's say, delta L1. And this plane at which there is no change in length is known as L1. This L and this L are same, and that is known as neutral axis plane. That is known as neutral axis plane. Let's do this. So now you understand what is this neutral axis plane. Okay, fine. Now, and this is what is the bend radius. This is what the bend radius is. This is how you want to bend, and you want to make that stay there. You don't want to come back. It should not rebound. You are trying to bend like this, and again it should not go up, right? So that is what you have to do. And so here what we have to understand is that, so there should be some kind of allowance has to be given for the bending operation. Okay. So what is the allowance for bending operation? This is a very important formula. I don't know maybe they'll be asking this kind of a question in HL or not, but it's very important in GATE. Okay. So the allowance, the bend allowance that you have to give is theta into R plus KT. So what is theta? Theta is nothing but the angle, bend angle that you are trying to bend, into what is R? Bend radius, the radius that you are trying to achieve, bend radius, plus K. What is K? K is nothing but some stretch factor. Okay, K is stretch factor, and T is thickness of the sheet. Okay, what is theta into R? Sorry, R theta. What is R theta? R theta is nothing but the length of this curve. Am I right? R theta is this length of the curve. Am I right? Curve length. Right. So there is some extra that you have to provide, so that the rebound also is calculated. Obviously, we try to if you want to have this kind of bend, so if you bend exactly this, that's not going to be, because of some kind of elastic recovery, it will come back again like this. So you have to bend little more, right? Then not will come back. So that extra KT will give you that allowance. So that's the reason why, what is the bend allowance you have to calculate. This is what is theta into R plus some KT. You have to make that, so that much of bend, so that that much of, because obviously this theta into R will be this curve. Theta into R plus KT will give you little more curve, little more bend will happen, and that is what is allowance. It will come back, rebound. Are you understanding my point? Yes, very good. So very important formula that you have to note for the bending. Very good, very good. Now let's proceed. And we have seen already, I explained this clearly. I'm not going to explain it again. So we have different type of bending. This is view bending. This is, what is this? Edge bending. This is edge bending. And this is view bending. Fine. And very important operation that we are going to discuss is punching and blanking. If you are not knowing the punching and blanking, please listen carefully. If you already know, again please listen carefully, because some of the points you might not noticed if you have read on your own. Okay, so this is very important topic, and people often get confused differences between punching and blanking, and sometimes they even get confused where we have to provide the clearance, where we have to give the shear. All these things will be very tricky for some people, not for everyone. For some people, the people get some students I've seen, some people are getting confused with these things. Okay, let me teach this in such a way that you never forget, or you no need to remember. Okay, so let me discuss this in a clear way. So there is, first we have to differentiate between this punching and blanking. So what is punching and what is blanking? Anyone who knows the difference between punching and blanking? Are both the same? What do you say? Okay, punch is hole. Okay, what is blank? Blanking? Blanking is a revolve part. Fine, it's a good thing. Good thing that what you have told is very right. Okay, so let me discuss here first, and then go to the another slide. So the discussion starts here. Okay, if you have a sheet, and you are making a hole onto the sheet, right? And the part where you made hole, that is also your, this is part one, because initially it is full part and then you made into hole like this. This was also a paper initially. Let's say this was a sheet. Now the thing that you removed after removing the after making the hole, the sheet what is left is the final product. So this is the useful one. This is useful, and whatever you removed is not, it is scrap. It's not useful. Then this is known as punching operation. Then it is known as punching operation. The other one is blanking. It means this is full sheet, right? And you made a hole. This is discarded. This is scrap. The other part is scrap, and this is useful. This is useful, and this is known as blanking operation. This is useful. So this is the difference between punching and blanking. So so if you want to understand this clearly, I'll tell you the example. General punching that we do on the paper, it's punching only. Why? Because you have A4 sheet like this, and you punch it like this, holes, and you use this, right? You won't discard this. This is useful. Right? This paper is useful. Whatever the punched residue, yes, the punched residue is there. The residue is will be that whatever the punched residue will be collected into the cage under the punch machine, right? So that you'll try to discard it, throw into trash, right? So this is punching. Any example for blanking? Any example for blanking? If you can think of anything. Any example for blanking? Yes or no? Where after removal of after punching or after shearing operation, the removed part is useful. Yes, you can think of coins. You can think of coins, but coins are made by using coining operation. But anyways, okay, you can think of like that, because on a piece of sheet you are making some coins like this. It's true. Or else one silly example. This might not come under sheeting. What you say, the sheet metal operation. Have you ever seen when we were kids? On our textbooks, we used to make this sticker, and that name, roll numbers, class, whatever will be there, right? The sticker used to have some sheet, and it should be like this. All the stickers used to be like this, right? Right? And then you use the sticker, and the rest of the part you used to discard. Remember these things? Yes or no? Yeah. So that is what is blanking. You are using the important part, the in between, the punched one. The other part you are trying to discard. Okay, fine. Fine. So now that you understood the differences between punching and blanking, let's discuss the punching operation. Okay. So for punching, Obviously, like deep drawing, you have to have die. This is die. Obviously, it's a circular thing. Okay, please try to understand. If you're looking from the top view, everything is a circle. This is circle. This is circle. Everything is a circle. Please to understand that it's not circle, or maybe it can be a square one also, but it's not. Maybe it can be a square like this. It can be a square thing also. From top view, it will be like this, and this is what is your complete die. Okay, on that you're putting some kind of sheet like this. This is your sheet. This is your sheet. Then you're trying to punch it from the top. Okay, fine. Now, so if you want to draw a precise diagram, then we'll draw something like this. Your punch, and this is your sheet, and 1 minute. This is your, what is the die? This is die. This is punch. You're trying to understand. Okay, and this is your sheet workpiece. Okay. Fine. Now, please, very important, you have to understand that. Now, after you want to make a hole into this, you want to make a hole in the sense you want to shear the material. That is how the metal is being cut. In metal cutting also we have seen, if you're trying to apply cutting force onto the workpiece by using tool, then the cutting operation is occurring with the help of shearing. If you remember, the shearing was happening, right? The shear angle also we have seen, if you remember. Fine. Now, this is what is die, and this is the punch here. Now, if in punching, please try to remember, in punching, obviously this punch size what you're having is less than, this is less than this die size. Die size is nothing but the diameter of the die, diameter of the internal die, the die internal die, right? So this is die size. This is punch size. So the punch size is less than the die size. In the sense, that's the reason why if you see this diagram is apt, right? So the punch size is less and die size is more, and the differences between punch and die is given as clearance. Right? So the basic requirement of punching is punch size should be less than the die size. And what should be the punch size? Punch size should be the hole size. The hole that you want to make is punch size. If you want to make 2 mm of diameter of hole, then the punch size that you have to select should be equal to 2 mm diameter. And then on that extra, you have to provide some clearance and make that die size. So, very important point is that punch size should be less than die size, and punch size is equal to the hole size. Punch size is equal to hole size. Hence, die size is equal to punch size plus 2 into clearance. Why it's 2? Because this side, if you're taking on top view, obviously this is your punch size, let's say, and this is your die size, let's say. This is your die size. Obviously, the clearance is 2. This is 1C, and this is another C. C. The total will be what? Die size is equal to 2C. Die size is equal to 2C. This C and this C plus the punch size. The punch size. This is the punch diameter. So diameter of punch. So that is what I have written. Die size is equal to punch size plus 2C. Is it clear, guys? Is it clear? Please try to remember, punch size is less than die size, and punch size is equal to hole size. Die size is equal to punch size plus some clearance, that is 2C. Yes, good. Now, so what is shear? Okay, let me okay. If you see your punch even with the paper, it will not be like this. It will be something like this. Yes or no? It will be like this, right? It won't be like this. Am I right? Yes, right? There will be some kind of, yes. And this is what is known as shear that is trying to provide. That that inclination that you're providing is known as shear. Why you're providing? Why you're providing? Please, if you're having a paper, like this, your punch is exactly like this, and you're trying to apply force onto this. Evenly, the punch force will be applied onto each. Evenly, it will be applied like this, like this. So initially, when the punch is completely in contact with the sheet, the sudden increment in force will occur, right? Because there was, if at all, I will show you like this. Okay, it won't damage the edges, because till immediately when this punch is touching the sheet, till then, let's say this is 4 time and force, till then it was 0. Suddenly there will be increase in force. Suddenly there is a spike at t is equal to 0.1. Why? Suddenly all the punch edge is coming in contact with the workpiece, right? And that suddenly that increase in force will be there. Okay. So now, instead of doing that, if you are having a sheet like this, and then if you are having this kind of shear, then slowly, initially, this will come into action. What happened? Okay, it got stuck. Let me wait for a second. Okay, it left. Yeah. Okay. Now, so initially this tip will come into picture, and slowly this, then finally this. In the sense, the force will gradually increase. It won't suddenly increase. Are you getting my point? So this is with shear. This is without shear. Is it right? Yes. So that is why you provide this shear. So to make complete hole, what you have to do? You have to pass this complete shear. Obviously, if your sheet is like this, and if this thing is like this, if you are making half the shear, obviously the hole is not full. Only when the hole is full, the hole is full when the complete shear is in like this, right? Then only this full hole has been occurred. So even though in knife also, have you ever seen a knife like this? Every time, have you ever seen a knife which is like this, it's handling like this? No, you'll be seeing a knife which is like this. Am I right? Right? So this is what is shear. Right? So this is without shear. This is knife without shear. Right? If you want to stab someone in the sense stab a fruit. Okay, if you want to stab a fruit, it's a fruit like this, you want to stab it. So it's better to stab a fruit with this rather than this. Am I right? Yes. Yes. That is what is shear. You have to provide that shear, and that shear is I, that has been given in this left hand side of the page. This is what is your shear. Okay. And now this shear is provided to punch. In the sense, your punch is not like this, your punch is something like this. And this is what is your shear height. The distance. Okay. Fine. So please remember important points. Punch size is less than die size. Punch size is equal to hole size. Clearance is provided onto the die. Obviously, die means die size will be more. Clearance is provided onto the die. Punch is always is equal to hole size. That's the reason why clearance is provided onto the die. And then that's the reason why die size is equal to punch size plus clearance. And then shear is provided to the punch. What is shear? This kind of inclination is provided onto the punch. So instead of having punch like this, you are trying to provide punch like this. That's it. Clear. Now let's go into blanking. So blanking is like this. Here, die size is equal to blank size. Okay, sir, I didn't get, sir, what is this die size and blank? Because now you are having something like this. This is your die, and this is your die size, and you are putting some sheet onto that. And then your punch is coming. Now that what they're trying to say is that this final blank that you want to manufacture is equal to the die size. Final blank, obviously you wanted some diameter, and that will be equal to die size. Okay. So hence punch should be less than the die every time, because there should be some clearance between punch and die. So hence punch will be less. So hence from already die size is fixed. Die size is nothing but the diameter of the blank here. So punch is equal to diameter minus 2 into clearance. Is it clear? Diameter minus 2 into clearance. Is it clear? So if you see this diagram, this is what is. So this die size is equal to the diameter of blank, and punch you made little smaller. That's the reason why punch size is equal to die size minus 2 into clearance. This is what is clear. So hence clearance is provided to whom? Clearance is provided to punch here. In the previous one, clearance is provided to die. Here clearance is provided to punch, and shear is provided to die. Here shear is provided to punch. No. Here how, sir? How can I provide shear? Because you just make this kind of arrangement. This kind of arrangement with the die. Right? Then you punch is same. Then you try to punch. Is it okay? So shear is provided onto the die here. Shear is provided to die. Yeah, it's vice versa only. It's vice versa only. Yeah, right. So very important points. So this is die size is equal to blank size. But please remember, die size is equal to blank size here, and here punch size is equal to hole size, because here after making hole should be precise. Here after making hole in the sense blank should be precise. That's the reason why blank is equal to die size here. Very important point here. Okay, fine. So now I hope I made this both the operations a little bit clear, right? Not I didn't discuss in detail, very much detail, but I hope you understand the concept of it, right? Yes. And so here it's clearly written. So this is your punching of what is a, yeah, this is punching operation, and this is blanking operation. And the clearance sometimes you decide by this formula, that is 0.032 into thickness of sheet. What is thickness of sheet? The sheet thickness that you're trying to put here in between the punch and die, right? That is thickness of sheet. And tau is nothing but the ultimate shear strength, because everything is happening because of shear only, because you're trying to apply a force parallel to the face that is going to shear. Like if you want to apply a force like this is shear, this is the face on which you're trying to apply, and this is shearing operation, right? So this is the formula is used for calculating the optimum clearance. And if you want to calculate what is the maximum force that is used, so area of shear. What is the area of shear? So let's say this is the blank. So now this is the blank that you have produced. This is the blank, right? Now you want to try to calculate the force. So obviously it is something like this, let's say. So this is blank. So you have to calculate the area of shear. Where the shear is occurring? The shear is occurring onto the surface of the blank, right? If it is like this cylinder, this is what is shear, right? This is the shear, area of shear. What is the area of shear? This is the diameter d, and this is thickness t. So what do you want to, how to calculate the circumference of this? Circumference of this is already it is pi d. Pi d is the circumference of the circle into thickness t will give you the area of shear. So area of shear into shear stress. Area into stress will give you force. Okay. So that is how you are trying to estimate the load of punching or blanking. Okay. Next. What is work done? Work done is nothing but already you have calculated force here. Now you are trying to calculate force into distance. And what is the distance that you are trying to travel? It's very important. Initially, it is like this, and this has to go. I told you already, it has to go like this, and it has to like this. So how much is the distance it has traveled? So let's say if you are taking this as your reference, the distance it has to travel from here to here, right? This is the end point. This is the starting point. This is the end point. So what is the distance between these two? Initially, it has to travel I. right? And this is your some penetration into thickness. If this K is equal to 1, if it is full penetration, full penetration. If K is equal to some value, then it is not. K is obviously cannot lying between 0 to 1, lying between 0 to 1. So if K is not equal, K is equal to 0, there is no penetration. If K is equal to 1, it's full penetration. Okay. So this is complete distance. I plus KT will be the distance that this punch has to travel so that the shearing operation is occurring. So hence force into the distance will give you the work done. So this is the work done that is required for the punching or blanking analysis. Okay, that is the reason why we write KT plus I. Okay, next. And this is how I told you already. Shear is one of the reasons why you are trying to reduce the punch force. I told you already, right? Okay, and that's the end of metal forming. That's the end of metal forming. So now, if you have any doubts here, you can ask me. But some 5 minutes. It's 6:55 now. Till 7, we can discuss some doubts that you have in the metal forming, and then we'll go into joining process. In this section, if you remember, in forming I didn't discuss any questions. So what I will do is that I will complete the syllabus little, so that because if you're trying to do more and more problems are thousands of problems are there. So it's better to discuss concepts rather than to discuss some 2000 problems. So because we have limited amount of time, we will solve the problems. I'm not saying that we are not going to solve the problems. We'll solve the problems, but let me complete the concept first. So in metal casting and metal forming, metal cutting, we have discussed the concept along with the problems. In this metal forming, I haven't discussed any problems here. So let me complete the welding also, the joining process. After that, I will take one complete session, maybe half the session, maybe one complete session for problems in both metal forming and the joining process. Is it okay? Yeah. Okay. Fine. So this is the end of metal forming. Let me open welding. Okay. Before starting welding, you have any doubts in metal forming? I'm here. You can ask me any question. Yeah. Any doubts? So how is the session going on? Till now we have completed 3 topics: casting, cutting, forming. Everything is fine. Are you able to grasp the things in this space, guys? Okay. Because it's very important you understand the concepts. Anyways, I'll give you some practice questions. You'll be able to solve them. I'll provide the key, and very easily you can solve them. If you have any doubts, please do post that in the group. I never see any questions that are being posted in group. You should be able to uh, ask the questions. It's not like obviously no one can answer all the questions. You'll be having some uh, problems or issues when you're solving some problems. So obviously you should be able to take a snapshot of the question and then post it in the group. Somebody will be answering the question, or if not, then I'll be coming up and answering the question, whichever is first you can take the answer. Okay, guys. Okay, fine. So now let's discuss um, the another topic in the manufacturing section, that is joining process. It's also known as welding. So welding definition is very nicely written in this three lines. I took it from some book. I don't know which book I forgot. It's a very nice definition. It comprises into very smaller understanding. I mean, the bigger understanding is put into very small sentences. That is what I mean. Okay. So what is definition of welding. Welding is a process in which localized permanent joint can be produced with or without application of heat. With or without application of heat, in the sense, some kind. What is welding? Welding is nothing but you want to join two sheets, two plates, two objects. Right? Where do you see? You see welding in every aspect of our life. You see anywhere. You see welding. Welding is very much required. You can't assemble a very big product in one manufacturing plant, and you can't export to some other place. Obviously, you take part by parts and then you try to assemble them in the location site of the. Let's say if you want to, you have a big machine. You have some big machine. Let's say big machine, or maybe what is a good example? Okay, have you ever seen this electrical poles like this? Some kind of electrical poles like this. Some kind of, but power transmission wires will be there. Have you ever seen these things? Yes or no? Yes. So now this kind of big object, you can't manufacture, you can't assemble them in the workshop, and then you take it you put it on a big container, and you can't transport these things. What you do, you take all the trusses, and then you try to assemble them. Then when you are trying to assemble them, you'll be using welding, right? Joining process. So that is what is joining. And this joining process can be done with the help of heat. In the sense, you try to heat the workpiece, and then you try to join them. And without application of heat also, you can be able to join them. Then we'll see what are the examples with heat and without heat. And sometimes you need to apply pressure. Sometimes you have to apply pressure. That's the reason why with or without application of pressure. Sometimes after there's a plate, then you have some welding done. Then you have to apply some pressure. See, sometimes there is no need of any pressure. Just try to put something like this and then keep on welding it. Keep on welding it. There is no point of applying pressure. Sometimes you need pressure. Sometimes you don't need pressure. Next is filler material. Filler material is in a sense extra material that you have to provide to join two different two objects. Okay, two materials. Let's say. So if you have this kind of plate and you have this kind of plate and you want to join these two, so obviously you need to fill with this extra material. Extra material is required. That extra material is known as filler material. Sometimes it is required and sometimes it is not required. Without that, you will be able to join the plates or material. So that's the reason why with or without application of heat, with or without application of pressure, with or without application of filler material. And also this welding can be used, or joining can be done between similar materials and dissimilar materials as well. Okay, so that is the definition of welding. And the welding welding or joining process can be categorized into these things. One is mechanical bonding, and this is where you do your analysis, or you do this mechanical bonding in machine design. Is machine design going on? I think machine design classes are going on, right? Yes, right. So in machine design, what you do, this mechanical bonding. So there are some temporary bondings and permanent bondings, right? So in temporary bondings, you use some screws, because if you want to join two different like this, you just put a screw like this and you close it. And if you want to discard, you open the screw and take it. So this is your joining process is temporary. You want to remove, you can attach if you want to attach. But sometimes they are permanent and semi-permanent. So this rivets, stitches, staples, all these things are coming under permanent and semi-permanent. In the sense, riveting is nothing but you're trying to put some kind of this thing, rivet you put, and then you close it like this. So this is a riveting. Stitching, you're stitching it. So if you want to remove, discard, or you want to make this bonding to break, or you want to remove this joining, so you have to break this joining element. In this case, no need to break this joining element, no need to destroy the joining element. You can happily remove the nut and you can remove the screw. But in this kind of rivets, stitches, staples, and string pits, you have to damage, you have to break the joining element. That's the reason why they are coming under the permanent or semi-permanent joints. Fine, that is where everything. Now this is where our interest is. That is the atomic bonding. This is very important, and this is what we are going to read. Okay, so it's atomic bonding. So in the sense, the bonding is occurring atom by atom, atomic level, at atomic level, right? In that we have solid state, liquid state, and solid cum liquid state. And solid state we have cold welding, friction welding, diffusion welding, hot force welding. Again in cold welding, pressure welding, ultrasonic welding, explosive welding, all these things are there. Okay. And liquid state, in the sense your liquid metal is being formed. Obviously here solid state, there is no liquid metal. Here liquid state, in the sense you have liquid metal that is being formed. So in that we have two categories: electric welding, chemical welding. In electric welding we have arc welding, electric induction welding, electric resistance welding. Gas welding and thermite welding will come under this chemical operation. Brazing, soldering, adhesive bonding will come under semi-liquid state. Okay. So in this syllabus we have arc welding, resistance welding, gas welding, thermite welding, brazing, soldering. Sometimes we discuss about explosive welding, ultrasonic welding, right? All these things we'll be discussing in the coming slides. Okay, fine. So welding is classified into three, okay, based on the composition of material. Okay, what is the composition of material, right? So one is autogeneous welding. If you see, this is autogeneous. What is autogeneous? You are not using any filler material. No filler material is used. Not filter, filler. This is filler material. So autogeneous means no filler material is used. Extra material is not used to join any two objects. Okay, and it is as you are not putting any filler. Where is my cursor? Okay, fine. So the example of autogeneous welding is solid phase welding, or maybe you can use as resistance welding, because you're not using any filler material. So sir, what is this resistance welding? We'll come back when we are discussing about resistance spot welding and resistance welding. You'll understand that there is no requirement of any filler material. The material, let's say that there are two sheets that you want to join them, and then you are applying some current. Obviously, there is some kind of a spot formed, and because of joule heating, and you try to apply some pressure, and because of that you're stitching it. There is no extra material that you're adding. That's the reason why resistance welding will come under autogeneous welding. Autogeneous welding, I tell you again, no filler material is used. No filler material is used. And what is homogeneous material? Obviously filler material is used, and that filler material what you're using, this filler material what you're using is same as parent material. In the sense, if you're trying to join two plates of mild steel, let's say, the filler material what you're trying to add in between should be also be mild steel. Should also be mild steel. Same material. Then the same material, that's the reason why it's called homogeneous welding. Right? And what is heterogeneous welding? Heterogeneous welding is nothing but you're trying to join two different objects, and these plates might be similar or dissimilar, doesn't matter. Let's say these are similar, and you're joining these two plates of similar material with the help of some other material. This is material 2, and this is material 1, and this is material 1. So these two plates are joined with the help of some other material 2, and that's the reason why this is called heterogeneous welding. Okay. So the example for heterogeneous welding will be soldering and brazing. I'll tell you why. Because you just join some plastic or plastic circuit boards with the help of some other material which are known as solders. All these things. The composition is different, right? Brass and all you'll be using, right? Fine. Next. And these are the different type of joints, and you'll be seeing these joints in your machine design as well. That is, this is your butt joint. What is butt joint? You have two different plates like this, and you're trying to join them. You're trying to join them, right? And this is what is your butt joint. Parallel, side by side, you're placing your plates, and then you're making some groove, weak kind of groove, and then you're filling it. That is what is your butt joint. Corner joint, this is your corner joint. You are filling it the corner joint. T joint, right? And this is your lap joint. Lap joint means overlapping plates like this. Lap joint. So you join here, and the plate is extended. Okay, this is in 3 dimensions. Please remember this is in 3 dimensions. Okay, and another joint is edge joint only, and that is what is like you see. This is where the joint is happening at the edge. Fine. These are the different type of joints that you have. You can use or you can make of. And let's discuss something on terminologies of welding, and also we have to discuss something important geometrical aspects of what you say welding sections. Like in welding, if you are doing the welding, there are some geometrical aspects which will come into play. So we have to know and we have to understand the terminology as well, right? So let's discuss that. So if you see here, so this is the butt joint. Obviously, you have plate 1 and plate 2, and you have plate 1 like this, and you have plate 2 like this. Okay, something like this, and you are trying to fill it like this. You are filling. Okay. And when you're trying to fill, it means that you're using a filler material. If you're using a filler material, what kind of a welding is it called? If you are using a filler material, what kind of and also please remember these two are of same material. Same material. Same. Yes, homogeneous welding. Please. Very good. Fine. So now this is where you're trying to fill the material, and you're trying to fill the material with the help of heat. It means that you're applying heat in this case. Liquid metal heating. After heating only the metal will be converted into liquid stage, right? And this is called yeah, and this is called the weld pool. Okay, or weld puddle also they say. Okay. Now after solidifying, this is how it look like. An extra protrusion that is being formed here, and that extra protrusion that is known as reinforcement. The protrusion that you get here is reinforcement here. And please remember, this is a cross section. Okay, this is a cross section. Please remember, the full weld is like this. Okay, please, this is a cross section. That's the reason why I've taken it in a shaded way. And this full part, this kind of a part is known as weld bead. Okay, weld bead. And the top one is called reinforcement. Already I told you. The bottom one is known as penetration. It is going into depth, right? So it is penetration. The cross-sectional area of reinforcement is AR. The cross-sectional of penetration is AP. So there is one term that you can define that is known as dilution. Like casting yield. Have you seen casting yield? What is casting yield? Anyone? It is a ratio of what? Hello? Remember what is that casting yield? Guys, now volume of casting divided by volume of casting plus volume of getting elements, isn't it? Remember this? Please go back and revise. This is what is casting yield. Yes. In the similar way, here also this dilution is nothing. It's similar to the casting yield. Area of penetration. That is what is important, right? You want only this. You don't want any reinforcement. But reinforcement will come. The area of reinforcement plus area of penetration is known as dilution. Okay. Fine. And coming to the geometrical terminology, this is the thickness of plate, obviously. And when you're joining the plates, you leave a gap here. And this is known as root gap. Okay. Why you are providing this root gap? So that if you are having something like this, then what is strength? Have some root gap. The strength will be good at the bottom of the joint. Okay. This is for butt joint, please remember. Okay. Now this is called fillet joint. Okay. So fillet joint is like you have some plate like this, you have another plate like this, right? And you are filling it like this, filling it like this. Right? This is all filling, right? So when you once you are filling, this is the cross sectional view. This is the cross sectional view here. So the contact between weld. So this is full welding, right? This is full welding. The contact between the weld and the plate is known as toe. This is toe. This is toe. And this is your weld face, the face of the weld. And the deeper connection, like this, you see, the deepest penetration at this point is known as root. This is what is root. Okay. So instead of assuming this to be like this, I assume this to be a straight line like this. Actually, it should be like this, but I'm assuming it to be a straight line, and that is what I have written like this. Okay. So if you see here, this is root here, and this is your weld face. This is your weld face. The shortest distance between, or the perpendicular distance between the root and the weld face is known as throat. The shortest distance between the root and the weld face is known as throat. The throat is very important in the point of mechanical loadings. If you are trying to apply some mechanical load like this and maybe something like this, the throat is very important because that is the weakest section where it can try to break, because that is the very smallest distance. No, it might break off at the cracks. The propagation of crack might occur at so and so positions. Okay, so that is what is throat. And I tell you again, if at all machine design classes are going on, this throat, root, all these things will be discussed in the machine design as well, because you have to design all this welding, the strength of the weld. You have to design all these things in the machine design. Okay, fine. So all the things whatever I have discussed are written in words here. Weld pool, right? Pool, the liquid metal in the in between the two different plates. Bead of solidification, it's known as bead. Reinforcement, the top protrusion. Penetration is inside. The root gap is given because to maintain the strength at the bottom. So is the junction between the weld face and the workpiece. Root is the deepest penetration of fillet. Throat is the perpendicular distance, or the minimum distance between the root and the weld face. Weld repulsion ratio is nothing but how fast you are going. If you are having two plates like this and you want to join these two plates, let's say. So now you are trying to weld, and how fast you are going is known as weld repulsion rate, right? Repulsion rate in the sense how much mass or how much volume you are trying to deposit in between that per time. Okay, till here the welding terminology is done. Then we'll discuss something about uh, techniques of welding. And this is your first technique or welding method, that is your gas welding, and it is known as oxy-acetylene welding, and this welding will come under chemical welding. So initially we have seen, right, the classification, see, chemical energy is used, and this is what we are discussing. In gas welding we are discussing the whatever the arc welding that we are trying, not arc welding, the gas welding we are discussing. In that we are discussing oxy-acetylene welding. Oxy-acetylene welding. Okay. So here, okay, let me explain with the help of diagrams. Let's not go in depth. In the sense, I don't want to read all the stuff. It will be very boring for you. I'll tell you all the concept with the help of this diagram that I have put here. the schematic diagrams. Okay, fine. You might have seen this welding, isn't it? In your day-to-day life, you might have seen this. Somewhere around, you might have seen this. You have two gas cylinders, the cylinder number 1, cylinder number 2. This gas cylinder is filled with oxygen. This gas cylinder is filled with acetone. In that you are dissolving acetylene. Okay, it doesn't. This is full oxygen, pure oxygen. It's okay. As acetylene is, you can't directly save acetylene in a cylinder. First you are putting acetone, and again in that acetone acetylene is mixed. So that's the reason why it's called as oxyacetylene, because you are using oxygen and you are using acetylene. Oxygen is O2, acetylene is C2H2. Okay, fine. Now from there, two pipes are drawn from that, and these two pipes are attached to some kind of a mixing chamber here. This is a mixing chamber, and there are two valves to control the percentage of oxygen and the percentage of acetylene that is coming into the mixing chamber, and some ratio of oxygen and acetylene is coming into this mixing chamber, and they are getting mixed in this chamber. And this mixed gas is coming into the torch. This is the torch, and this is kind of a nozzle. If you see, this is kind of a nozzle, right? And as the gas is coming out, you try to ignite with some kind of ignition. When you ignite, some flame is coming to picture, right? Some flame is coming, like your gas cylinder, right? In your home, you might have seen. Just use the put the gas cylinder on the stove, then use some matchbox, and then you ignite the burner, right? The same way, this is the flame, right? And that flame is used for heating the workpiece and as well as the filler material, right? It is trying to heat the workpiece as well as the filler material. And if you are using the filler material of same material, then it is called homogeneous. If you are not using the filler material of same material, then it is known as heterogeneous, if you remember. Now, fine sir, how this flame is coming? Where the chemical reaction is occurring? Yes, chemical reaction is occurring at this tip. How? Because what is coming? Some C2H2 and some oxygen. Both are mixed, and you are trying to ignite them, and then this reaction is formed. So CO2 is formed, H2O is formed, and good amount of heat is formed. This is what we'll be using. Because of this reaction, C2H2 plus O2 with some parts, 2 parts of C2H2 and 5 parts of O2, whatever it is, that is full chemical balance you have to do, chemical reaction balancing you have to do. And good amount of heat is coming. This heat is used here to heat the workpiece material or filler rod. Okay, and that is what is oxyacetylene welding. It's simple, very easy, but we have to understand some different aspects of it. Very important. What is that? Here we have selected C2H2 and oxygen. Why? Why, sir? We can select any other thing, some other things also. We just use LPG. Directly you burn it and use that LPG. I can use that, but we have selected this kind of combination so that CO2 is produced. Why CO2? Why sir? Why we are using CO2? I don't see any point in using CO2. We have to use that CO2. Why? Because if you're heating the workpiece, the workpiece is heated, and atmospheric some oxygen is there. Some some atmospheric oxygen. Obviously, some atmospheric oxygen will be there. And once some metal is heated, the atmospheric oxygen will come and attack the fresh workpiece metal, the liquid metal, because if the oxygen is having this tendency to oxidize the material, and it is very high at high temperatures, right? Oxidation is very high at high temperatures. So if it is coming into liquid, the oxygen is attacking and it is making this layer impure by oxygen forming this oxidation. So to prevent this oxidation, what you do, as you are selecting these two, the CO2 is spread. The CO2 is around this flame, right? The reaction is happening. CO2 is around this flame. H2O is around this flame. Heat also is around this flame. the CO2 will act as a layer, as a protection layer, so that this atmospheric oxygen is not affecting the workpiece and it's not oxidizing it. So that's the reason why the CO2 is very important. Are you getting my point, sir? This is the second point. See, this burning also produces carbon dioxide, which helps in preventing oxidation of metals being welded. Okay, fine. Now, okay. So why will it? Why we are using acetone and then mixing acetylene? Because acetylene is very dangerous under its own weight, so it can explode. So you fill in calcium silicate and then acetone, and then acetylene is absorbed into acetone. That is the reason why these are some chemical reactions that are happening inside, so that acetylene is not directly filled into the cylinder. Acetone is filled, and then acetylene is absorbed into acetone. That is what you have to understand. Okay. Next. So these are the reactions that are happening. I've just written the final reaction here. I've just written the final reaction, but the reactions are in intermediate stages. The primary reaction is C2H2 acetylene plus O2 give rise to 2CO carbon monoxide plus hydrogen, and this C2H2 will come here. This here 2 as mixed with some amount of extra oxygen because oxygen is there, and then the CO2 and H2O and whatever the delta H2, whatever. So this delta H2 is the heat that is used for heating the workpiece of welded material. So finally, if you are combining these two reactions, primary and secondary, the final reaction is coming out to be like this. And this is what is important. That is what is heat. Very important. Okay, fine. Now, fine. These flames are produced. So there are three different types of flames we can get based on the composition of oxygen and acetylene that you are trying to provide to the mixing chamber. If you are having more oxygen than acetylene, then some kind of a flame is achieved. And if your acetylene is more than oxygen, then some kind of flame is achieved. If both are in equal parts, then some kind of flame is produced. So based on the ratio of oxygen and acetylene, there are three different type of flames that you can achieve. So what are the three different type of flames? The first one is nothing but reducing or carburizing flame. In the sense, your acetylene is more than oxygen. Your acetylene is more than oxygen. If you see, the oxygen is to acetylene ratio is less than 1, because oxygen is to acetylene is less than 1. Means what? Oxygen is less than acetylene, C2H2. So acetylene is more. That's the reason why this is the ratio of oxygen to acetylene is 0.85 to 0.9, which is less than 1. If this kind of ratio of gases are mixed into the mixing chamber, so this kind of flame is produced. In that flame, you can divide that into two things. Have you ever seen this kind of flames? Like there is some kind of a blue flame that is there. At the center, there is some kind of a red cone. Have you ever seen that? Have you ever seen that in any welding operation somewhere? Yes or no? Yes, in candles also. The outer flame will be different. Inner will be something else. Right? Inner will be something else. Okay. So the flame that is produced by this carburizing, the ratio of this thing, that the ratio of this thing is very what I'm saying is that I'm sorry. The thing is, the ratio of oxygen and acetylene is less than 1, right? So acetylene is more. So if acetylene is more, there is some thing that can happen. And also, please remember this inner cone. This inner cone is the one where maximum temperature is at it. You will be having. The outer one is simply a flame, some kind of a flame. But this is the place, inner cone. This inner cone. Let me take some other pen. Okay, this is the inner one. The interface between the inner cone and the outer flame. This interface will have maximum temperature zone. In what? In carburizing flame. Please remember. carburizing flame. Okay, so now, so and also you see the length is more here, the length is little less, and the length is in average in between these two. Okay, so let's assume length is more, this length is more. Why the inner cone length is more? Because if we want to burn, you want to burn what you want more and more oxygen, right? If you want to, some fire should be burning, keeping on going, means you have to provide oxygen, right? So as in this ratio, the oxygen content is less, and for burning in the sense of for the chemical reaction to occur properly, it needs some oxygen, and that in search of that oxygen, it is extending its, what you say, inner cone. It is extending its inner cone so that I want more oxygen, I want oxygen more. That's the reason why the reducing or carburizing flame will have more inner cone. Length of inner cone will be more in the case of reducing or carburizing flame. Okay. Now, where are we using this, sir? Okay, sir. We have different flames. Where are we using this? Why we have different flames? Why we are making one flame is enough? No. Why we are changing all this hangama is there? Yes, we have to change this composition because every material is uh, unique. If they have their own properties, they have their own carbon content, right? So this reducing or carburizing flame is used in alloys and steels and alloy steels and aluminum alloys. And where what you say, it cannot be used, where it cannot be used, anyone, guys? Hello. Acetylene is more, means carbon dioxide, carbon is more, am I right? Yes or no? Yes. So if at all, if there is some object, there is some object which is having some low carbon, and then you are trying to put this reducing flame, then what happens, the carbon, whatever the rest carbon will be depositing onto this thing and forming some brittle layer onto that. That is not good. We don't want that brittle because brittles are very easy to fail under tension. But if something is already having carbon, high amount of carbon, if some objects are having good amount of carbon in that, let's say, then the extra carbon which is there because of this acetylene will not make much serious action onto these high carbon steels, right? So this reducing or carburizing flame can be used for high carbon steels. Where is it? Where is it? Yeah, here. High carbon steels like cast irons. Cast iron will be in the form of, if you see the iron carbide diagram, the cast irons will be around 4.3% of carbon. If you see on the edges, you will be seeing that cast irons, right? Okay. And the temperature ranges will be this thing, 3100 degrees centigrade to 3300 degrees centigrade. Okay. And what you say, why we are using it for aluminium? Because aluminium is more prone for oxidation. So for oxidation you need carbon dioxide. For carbon dioxide you need carbon. For the good carbon you need to have C2H2, right? So that is the reason why you can use this reducing or carburizing flame for aluminum alloys. Okay. So please remember, reducing and carburizing flame is used for aluminum alloys and also high carbon steels. High carbon steels. Yes. Now let's go into another flame, that is oxidizing flame. Now we are going to the second flame here. Okay. In oxidizing flame, the length is very small here. If you see, the length is very small because already good amount of oxygen is there. There is no full proper oxygen is there inside itself because the ratio of oxygen is to acetylene is greater than 1. Oxygen content is more than the acetylene. As good amount of oxygen is there, the inner core need not to search for the oxygen. The length it has to travel will be little less. This is more. This is little less, right? And the temperatures that are generated in this flame are around 3400 degrees, 3000. Obviously, it will be more oxygen, more heat is generated, right? More oxygen, more heat is generated, right? That's the reason why it is 3450 degrees centigrade. Fine. And these flames are used, see, for copper, bronze, brass, zinc, all these things will be used. Why? Because these are what you say, um, low density materials, right? It's copper, bronzes, all zinc, all these things are low density materials or low melting point materials, and as they are low density, they'll be evaporated very easily, right? Because the evaporation is very easy, the material will be evaporated. So to avoid that kind of evaporation, what you do, you provide more oxygen. As you are providing more oxygen, what happens? There is some oxidation layer that is formed in the welding pool. So this is your welding pool. Some oxidized layer is formed. That oxidation, in the previous case, you don't want oxidation to happen. That's the reason why you're using this flame, because oxygen is less. In this case, you are using oxidized layers because you want the oxidation to happen, and this oxidation layer will protect this molten metal for avoiding the molten metal to evaporate. You don't want this molten metal to evaporate. Hence, you are allowing the oxidation to occur, and this oxidation layer will be protecting as will be acting as a protection for the evaporation of your alloy material here, whatever the material that is there in the weld. Okay, so that's the reason why you are using this oxidation flame for brass, bronzes, copper, and zinc, and all these things. Okay, fine. Next is nothing but neutral flame. A neutral flame. Here, if you see, the inner cone is in between. This inner cone length will be in between these two. So if you see the diagrams, let's assume that the inner core length of neutral flame is n. The inner cone length of oxidation curve will be less than the neutral flame. The inner cone length of reducing flame will be more than the neutral flame. So neutral flame is the reference point. This is the reference point. And with respect to neutral flame, the reducing flame inner cone length will be more. Oxidation inner cone length will be less. That is what is important point. Okay, fine. And this is used for low carbon steel, mild steels, and all these things, because they are having mild steel also is having low carbon steel. Okay, now, and the temperature is 3150 degrees centigrade, which is in between reducing and oxidizing flame. Okay, so here the ratio of oxygen and acetylene are in equal parts. Both are equal. That's why it's called neutral flame. Hope you're understanding this important points that I'm telling. Okay, so 3 different flames, and the different flames are categorized based on the percentage of oxygen and acetylene that you're trying to provide, or the ratio of oxygen and acetylene that you're trying to provide, and the materials, for which materials, which flame you are using, and the results also, right? You know the results also, right? Are you getting my point, guys? Hello? Yes, very good, very good. Now there are different type of welding techniques. One is known as forward technique, another is known as backward left hand or forward left hand or forward hand welding, backhand or right hand welding. What is that? We'll see. So if you see in this bottom thing, this is what is forward. Why it is forward? Because your flame is tilting like this, and you are moving in this direction, right? And the welding is left like this. Okay, so diagram itself is very self-explanatory if you are trying to understand, right? Because the flame is pointing towards the movement. This is the movement. Flame also is trying to product in the same direction, but in this direction, the flame is in this direction, and the welding movement is in this direction. Both are in opposite directions. So that's why this is called backhand, and this is known as forehand. And also here, if you see, The flame, which is this is already welded part. The red color part, whatever is seeing here, is already welded part, welded portion, welded portion. Right now, this flame, which is already it is towards the unwelded part. This flame is the outer flame is towards the unwelded form or unwelded part. This is unwelded, right? Unwelded. It's not welded. What is the use of this? It is preheating the material. It is preheating the material. This is preheating because this is the inner cone which is responsible for heating and melting. Outer flame is used just for preheating. Okay? In the other way, if you see, the flame is pointed towards the already welded portion. In the sense, it is reheating it. Here it is reheating the already welded portion. Here it is preheating the unwelded portion. So that are the two advantages of both forehand and backhand welding. Okay. So what is the use of preheating? You can reduce the residual stresses. What is the use of preheating? You can reduce the crack formations. Okay. So those are the important points for your forehand welding and the backhand welding. And these are the different welding positions that you can make the weldings. That is your horizontal position. You know already. This is your, what is the joint? What is the joint? Anyone can say what is the joint? The name of the joint? Name of the joint? Yes, butt joint. Very good. Very good. Butt joint. This one? Okay. This one? Yes. Very good. Very good. Okay, fine. Anyways, you're on track. Anyways, so you're just horizontal. In horizontal also you can do flat. This is also, it will come under flat also. Flat in the sense like you have some plate and you just flatly are producing it. Flat, horizontal or flat. Okay. And vertical is this, that you're going vertically. Overhead is like you are doing on top. You're on ceiling. On ceiling, if you want to join, then it is called overhead welding, and it is against gravity, obviously. Right? Fine. Now, okay, fine. This is the end of different flames that are being produced in gas welding. Chemical reaction is important. The flame is flame is generated because of the chemical reaction between oxygen and the acetylene. Hence, this is coming under chemical welding. And we have seen what are the different type of weldings: right hand welding, backhand welding, and what are the positions can be achieved by using this welding. And also, this welding requires filler sometimes. Filler is very important here because you want to join this butt joint or lap joint or whatever the joint that we have, you have to fill it. Obviously, this is known as homogeneous welding, or maybe if you are using different materials, then it is known as heterogeneous. Generally, it is homogeneous welding. Okay. Now, let's go to another sector for the chemical welding, that is arc welding. Not chemical, electric welding. This comes under electric what do you say, classification. See, electrical classification. In that we are discussing arc welding now. Initially we discussed gas welding. We are done with that. Now we are discussing this arc welding. Okay, fine. Okay, now, so here non-traditional machining process we have seen, right? Where did we use electricity? In what are the non-traditional manufacturing process that we have, non-traditional machining process that we have discussed, where electricity is required? Any example for that? What are the non-traditional machining process which requires electricity? Any example that you can tell me? Any process that you know? We have discussed, no, in the previous classes, where we have used water jet machine. Did we use electricity? Guys, come on. Did we use electricity here? Where did we use? Where did we use electricity? Water jetted machine is simple mechanical. We have some water, and we have discussed abrasive jet machining. Water jet is also same thing, similar. We're just using the pressurized water and we are trying to cut it. Where we are using electricity? What is the first non-traditional machining process that we have discussed in the previous class, in the previous lectures? Is it not ECM? We have discussed ECM, right? We have discussed EDM. Remember? In both the cases, we provide electricity and we told that workpiece and tool both should be electrically conductive. Remember? Yes. Electron beam welding is different. We are not providing electricity there. We are creating some good column of electron beam. We are not producing any, we are not providing any electricity. We are not making any terminals there, right? So EDM and ECM are the processes where we are using electricity as primary things. In this we are providing electricity, chemical reaction is happening because of production of electricity, then machining is happening. Here, because of electricity, some discharge of dielectric constant is happening, dielectric material is happening, because of that, again, material is neutral. Okay? So here also, we are providing electricity between workpiece and tool. And here in the case, the tool is nothing but this electrode torch. Tool is nothing but this filler material or electrode which is kept onto this electrode holder. Okay. Okay. So what is happening? You might have seen this thing also, arc welding. Have you seen that? Some kind of Diwali program will happen everywhere in the workshop, right? So where you have this workpiece, and you have some torch, some pencil kind of item, right? And this is known as electrode. This is known as electrode, and this is put onto torch. And then what you do? Initially, you rub like this. You give it touch. When you give it touch, the circuit is closed, right? Electricity is passed. Suddenly, you see that spark, and then you flipped it, and then you do the welding. Have you ever performed arc welding in your BTech days? Yes or no? Did you do this arc welding in your first, second, or third years of your BTech? Might have done this thing in your welding laboratory. Yes or no? Guys? Yes. Fine. So this electrode will be acting as sometimes as a filler material. Sometimes this electrode will not be acting as filler material. You have to add some other extra filler material. Sometimes the electrode itself is a filler material. Sometimes the electrode is not filler material. Some extra filler material has to be provided. Okay. Fine. So here this workpiece is given positive, then it is called anode. Electrode is given negative, then it's called cathode. Right? Sometimes you can do the reverse. You can give workpiece negative and electrode positive. That is known as reverse polarity. Whatever what I've shown here is a positive polarity. Right? Electrode negative, workpiece positive. If you're reversing the polarities, then it is known as reverse polarity. Then I'll tell you what are the reverse polarity and normal polarity. All these things I'll tell you. So what you do, whenever you have this workpiece and you have this electrode, when you are touching it, obviously you are giving some polarity to this circuit, right? When already circuit is there, when you are closing the circuit, electricity is being passed. Because of that, some series of sparks are generated, and then arc is generated. This arc is generated. This arc is nothing but it's a thermally ionized column of gas. Thermally ionized column of gas, and that arc is producing approximately 5,500 degrees or more degrees of centigrade. Temperature is generated. This is what is temperature. Where you are getting temperature? You are getting temperature in the form of arc. Right? And because of that arc, temperature is generated. Because of the temperature, workpiece is melted here. Workpiece is melted. And if at all electrode is having very low melting point, then electrode is also melted and deposited into this space. Right? So there are two different arc welding procedures that we are going to discuss. Those are TIG welding and MIG welding. TIG welding is non-consumable electrode. Non-consumable electrode in the sense electrode will not melt. Electrode will not melt. So if you want your electrode not to melt, so the electrode should be of high melting point material. High melting point material. Right? So that is the reason why we select tungsten as our electrode material, which is having high melting point. So that's the reason why it's known as TIG, tungsten inert gas welding. Okay, let's discuss that in the coming slides. Okay. Okay. So before that, we'll discuss how this heat is generated and how this electrode is being deposited, where more heat is generated, right? What is this arc length? All the things we have to discuss. Okay. So let me. Okay. Okay. So once you touch, circuit is closed, and then you lift a little bit. Arc is sustained. Arc is there. Arc is there. This arc is generating approximately 5,000, more than 5,000 some centigrade, because of that heat is there, and sometimes this heat is melting this electrode, and heat is melting this workpiece also, right? Okay. So if you are giving positive polarity, straight polarity, they say, that means workpiece is positive, and electrode is negative. Electrode is negative. Okay. So you are having this kind of circuit, right? This is your circuit. This is your power supply. This is your power supply where voltage and all these things are created. Voltage and current, everything is set in the power supply, right? Now, always, every time, please remember, every time electrons will flow from negative terminal to positive terminal. Anions will be flowing from positive terminal to negative terminal. Okay, please remember that. It means that if you exaggerate things, this is your tool, this is your workpiece, let's say, electrons will go from top to bottom. This is negative terminal, this is positive terminal, and this is workpiece, and this is tool, right? And anions will go from bottom to top. Okay. So the current flow will be opposite to this electron movement. So the current will be in this direction. Okay. Okay. Now, as the electrons are moving from negative terminal to positive terminal, and electrons will be having high velocities. Electrons will be having high velocity. And these electrons are having high velocity. So what happens? That will hit the workpiece with high velocity. Momentum is very high. Because of that, out of complete heat that is generated in between this electrode and workpiece, 2/3 of heat is generated at workpiece, and 1/3 of heat is generated at electrode. In a sense, what I can say is that 2/3 of heat is generated at anode, 1/3 of heat is generated at cathode. Here anode is workpiece in our case, cathode is electrode, and that's why this is called straight polarity. Polarity straight. Okay, fine. And I told you that there is a distance between electrode and the workpiece that is known as arc length. It cannot be very short, it cannot be very high also. It can be short, but it cannot be very high. If your distance between electrode and the workpiece is very high, the arc will not sustain. It has to have some gap, some optimum gap, so that the arc will be keep sustaining. The columnized gases will be keeping on sustaining, right? So that is known as arc length LA. And please remember, this arc length LA is very important, because voltage is directly proportional to this LA. Whatever the voltage that you're trying to provide is directly proportional to this LA. Okay, fine. All right. So whatever the points that I've discussed are discussed in this, points. Okay. Now let's discuss about direct current, straight polarity. Straight polarity I told you already. Direct current, DC, direct current, straight polarity. State polarity already told you. Positive workpiece, negative electrode. And next is direct current reverse polarity, that is negative, and that means cathode is given for the workpiece and anode is given to the electrode, that is positive electrode. In both the cases, if you see, 2/3 of heat is generated at workpiece, in the sense at positive terminal. If you see here also, 2/3 of heat is generated at the positive terminal, because wherever the positive terminal is there, it means that electrons are passing from here to here in this case. Here in this case, electrons are passing from bottom to top. Okay. Electrons are coming from top to bottom, good velocity is there, more amount of heat is generated at workpiece because of electrons, because this is anode and that is cathode. Right? Fine. That is very important point that you have to remember. Now, so which kind of materials we have to use, or which kind of setting can be used for which materials? So straight polarity setting, the direct current straight polarity setting can be used for high melting point materials. Why, sir? Because I want more heat to melt this material, right? So if you are using reverse polarity, more heat is generated at electrode. I don't want that. I want more heat to be generated at workpiece. If I want more heat to be generated at workpiece, I have to use this straight polarity. Okay? I have to use the straight polarity, so that at workpiece more heat is generated, right? And as lesser amount of heat is generated to the electrode, the deposition of electrode is very less. The weld deposition rate will be very slow. Okay, so those are the important points you have to take. That is what I have been written here and here. If you read these 2 points, what is that? Because of high heat generation at work, high melting point materials and higher thickness of plates can be joined. Thickness of plate is very high also, then good amount of heat will be required, right? So here straight polarity is used. And because of lower heat generation at electrode, because electrode is anode, lower heat generation is at electrode, at anode, the melting rate of electrode is low, deposition rate is low, and low welding speeds are. So as deposition is low, you can't move very fast. You have to go very slow. Welding speeds are very slow. Everything in the case of reverse polarity will be vice versa of this, mean opposite to this. Okay. So what is that? The same slide. The same thing will be in the next slide, but with different things. What is that? Electrode is positive and workpiece is negative. More heat is generated at what? Electrode. Because electrode is cathode now. And less heat is at workpiece, because electrode workpiece is anode. The electrode is anode and workpiece is cathode. Sorry. Okay. And because of low heat generation at workpiece, low melting point materials can be used, because if you are using high heat for low melting points, then it will be melted away easily and then it will evaporate. It's not good. So low melting point and lower thickness of plates can be joined using reverse polarity. And as heat generation is more at electrode, melting rate of electrode is very high and deposition also is very high. Because of that, good welding speeds are achieved. Okay, so that is what is the difference between the direct current straight polarity and direct current reverse polarity. And there is one more setting, that is known as alternating current. Alternatively, you will be changing the polarity. Sometimes positive straight polarity, sometimes reverse polarity, sometimes positive, sometimes reverse. Positive, reverse, right? Straight reverse. You will keep on changing the settings. That is what's known as AC. So that is that 50% and 50% of heat is generated anode and cathode equal, because half the time you are giving one pulse straight, another pulse reverse, one pulse straight, another pulse reverse. That is what alternating current. So as I told you already, more heat is generated at workpiece, hence more depth is achieved in direct current straight polarity. Lesser heat is generated at workpiece, that's why lesser depth of penetration is achieved at reverse polarity. AC is alternating, so it will be in between reverse polarity and straight polarity. Is it clear, guys? Yes or no? Hello? Okay. Very good. Now, So let's discuss this thing and close for today's session. Okay. So in arc welding, if at all you are using, if you are, if the deposition happens, this deposition of electrode is happening, it means that this is electrode is filler material, let's say. Then you have two movements. What is the first movement? Linear movement of electrode with respect to workpiece is linear welding speed. What is that linear movement? Linear movement is nothing but this movement. And this depositing, you have to move your torch in this way, right? This is movement number one. That is what is linear movement, right? Another movement is downward movement. Why? Because this is getting consumed like cigarette. It is getting consumed. So obviously you have to move this in this direction. Downward movement. That movement is 2. Okay. So this is first movement, welding speed, and downward movement is there. That is to compensate the electrode consumption and also to maintain this arc, right? So there are two movements, first movement, second movement. Now, if the two movements, these two movements are controlled manually, if you're doing it manually, then that is known as manual arc welding. Both this movement and this movement are controlled manually with human, then it is called manual arc welding. If two movements, this one movement and these two movements are controlled by machines, then it is known as automatic welding. If first one is controlled by human and this is by human, and this second one is controlled by machine, then it is known as semi-automatic welding. One movement is controlled by manually and second is by machines, then it is known as semi-automatic welding. Is it clear, guys? Yes or no? Fine. So let's stop for today and let's discuss these things from in the next class, and we'll be discussing what are the different type of machines in arc welding, constant voltage type, constant current type, and voltage is directly proportional to arc length, open circuit voltage, closed circuit voltage. All these things we'll be discussing, and in the next class probably I'll be completing welding in the first half 1 hour around, and in the another hour we'll be solving some problems in metal forming and welding as well. Okay, so fine. So let's not drag for more time because I have another class coming up. So if you have any doubts here, let me know. I'll be able to answer happily. If not, thank you.